Hello everyone, and welcome to Biopedia. This episode we will be adapting another blog post from a few years ago into episode format. However, this one is a little bit different as it's not based on any one specific source, but more just a general discussion. This is because today I thought I'd take a moment to discuss how exactly biologists create phylogenetic trees. Our discussions will not include factors such as morphological comparisons, etc., which were more widely used before genetics came along, but rather the molecular methods used today. So, let's say that you're an ecologist who's just discovered an uninhabited island far out to sea. There are 3 species of snake on this island, and you want to know how long ago these species diverged from their common ancestor. You find a fossil which tells you species A and species C must have diverged 15 million years ago, but you can't find anything for the other species. So instead, you sequence a protein common to all species, let's say hemoglobin for the sake of argument, to examine how many amino acids are different between the proteins in each of the 3 species. This gives you the following results. Species A and B have 11 amino acids of difference within the protein. However, species C has 30 amino acids of difference from both A and B. Okay, so how does this help you? Well, we know that, in the 15 million years since species A and C diverged, there have been 30 amino acid sequence changes between species A and C. However, this doesn't quite give us our rate of mutation yet. To know why this is the case, you've got to consider that both species have been evolving away from their common origin. This means that we've effectively got to double the time between them to 30 million years. After all, species A has been evolving on its own for 15 million years, and species C has also been evolving and changing for those 15 million years, leading to 30 amino acids of difference across effectively 30 million years of evolution. What we're trying to do here is establish how fast these amino acids change, roughly, to see if we can fill in the gaps. So, if we assume a constant mutation rate, we end up with a rate of 1 mutation per million years. What we've done is calibrate our molecular clock. We now know the rate of mutation for the protein we're using to build our tree. So, let's now look at the difference between species B and C, which is also 30 mutations. Given our rate of change, this means that these 2 species also had a total evolution time of 30 million years, as in 15 million years of evolution away from each other for both species. So, dividing by 2, we get a divergence time of 15 million years, as with species A. The real difference comes when we slot our 11 amino acids of change between species A and B into the general picture. Putting this together with our molecular clock, this means that A and B must have diverged 5.5 million years ago. How does all of this fit together? Well, it means that C must have split off from the common ancestor first, and then A and B diverged. Of course, there are some assumptions we've made while constructing our tree, such as assuming that there is a constant rate of mutation. Added to this, most phylogenies will be a lot more complicated than just 3 species. However, it serves well as an example of the process by which such trees are constructed. A more in-depth discussion of, let's say, these assumptions, the process of speciation itself, and the complexities around constructing these trees are good stories for another time. However, I thought this would be a good first introduction to the topic. So, that brings us to the end of today's episode. As always, thank you all for listening. Feel free to get in touch at the show's email address if you have any questions, comments, or topic suggestions for future episodes. Until next time, have a great week, everyone.